Okay, so welcome. Today we're going to be exploring the modifications of metals. In particular, we're going to be looking at heat treating. So basically what this means is, as you can see here, what I've written out is the properties of metals can be modified. Now, this allows metals to gain different characteristics. So say a metal is extremely soft, okay, and you want to harden it. There are methods in which we can use in order to change the properties of that metal. So in other words, from making it really soft, changing it from being very soft to becoming a lot more tough or hard. Now, the methods that we explore in VCE chemistry, there's three main modalities. So one of them is alloying. Now, there should be a video on alloying already, so we won't really explore this bit in today's tutorial. Then we go through work hardening. Now, work hardening, we'll look at this one, and then we'll look at heat treating. So one of the important things with modifications of metals is first to remember or to understand that metals are actually structured as crystals. They have a three-dimensional particular shape, 3D shape, which is known as a lattice. Now, depending on, so remember that metals are three-dimensional, okay? So if you took a very powerful microscope and you looked at the structure of metal, what you'll find is that metals are actually, and this is a metal that has been analyzed using a microscope, and you can see that there are different types of grains and crystals, as you can see here. Now, what you can see that metals are comprised or are made up of grains. And these grains, they're also referred to as crystals, but they can vary in size. So here, the crystals, you can see that each of these boundaries here, like if you take a certain boundary, that's basically called the grain boundary. And you can also see that that's one crystal, and that's another crystal that's smaller. Okay, so here you've got a smaller crystal. Now, the way in which we can modify the property of a metal is by essentially manipulating these crystal sizes. And with work hardening is actually just a process in which we modify metals by adding external force. So work hardening is adding external force. So you can think of this as, the blacksmith, for example. A blacksmith may take a hammer and may beat a particular metal with the hammer. And by doing this, it's actually a result of work hardening. Work hardening actually shatters crystals. So it shatters crystals. So if you look at that overall picture here, it actually it creates more boundaries between the crystals. So I'm just drawing these boundaries in. Imagine if I just took a hammer and whacked this metal, and basically it just shatters the metal into smaller smaller components. So if you've ever tried to do this, a good example is, for example, a metal spoon that you use to dig out ice cream from a from the carton. So you're digging out ice cream and the spoon's kind of twisting. Maybe you're using a metal spoon, it's going backwards due to the force that you're adding to it, and maybe you'll then adjust that spoon and try to put it back into its original configuration. So every time that metal spoon moves backwards and you push it back forwards, what you're doing is you're applying a work hardening on that spoon. So eventually the crystals within that spoon, the grain size is actually going to get smaller and smaller and smaller. And what that will actually do is it will make the spoon a lot more brittle. So that point that you're constantly adding pressure on, that you're bending and putting back into its own original shape and then doing that again and repeating that, it actually reduces the crystal size. Now eventually, if you eat ice cream enough, what's going to happen is when you use that spoon again, that spoon may just completely break at that point where you're applying the work hardening. And the reason for that is work hardening makes the metal tougher, so it makes it more stiff in that area that you constantly bend and reconfigure, etc. It makes it more hard, but it also makes it more brittle, because one of the things that will happen is as you shatter the crystals, and the grain size decreases. And as a result of decreasing grain size, you're actually increasing the brittleness of the metal. So as you're increasing the brittleness of the metal, the reason why you're increasing the brittleness of the metal, if you have small grain size, if all of these kind of get smaller and smaller and smaller in a particular section of the metal, so I'm just drawing these in here, if they get all very, very tiny and they start shattering, what will happen is, because there's a boundary between one grain size and another, so if you can imagine, I haven't drawn it in, there's atoms, and those atoms are pushing against each other. So each of the grain boundaries are actually pushing against each other, and it's making it more difficult to sort of try to bend the metal again. Okay, so as you're increasing the amount of grains and making them smaller and smaller, the friction between those grains increases. And what that does is it actually makes the metal in general a lot more brittle. It makes it hard because it's difficult to sort of try to bend that metal again, because the smaller the crystals get, and the more grain boundaries you have, the more difficult it becomes to bend that metal. So eventually, if you're trying to scoop up ice cream, that metal is going to get so it's going to be so resistant to motion that eventually it will just snap into two pieces, so that's basically what work hardening is. Work hardening is a process. It doesn't involve heat at all. It's just a process in which you're applying an external force. So maybe a blacksmith is beating the particular metal with a hammer, and you're essentially shattering the crystals and making them making the configuration of the metal lattice, you're creating smaller grain size. Now, so another way in which you can modify metals is by this method called heat treating. Now, heat treating is a lot different than work hardening. Work hardening, remembering, it's just applying an external force. So you're smashing a metal, or you're hammering it, or doing something like that. It doesn't involve heat. Heat treating does obviously involve heat, and this is all to do with how you are working with a metal. So there are three important heat treating methods that you need to remember. So one of them is quenching, the other one is annealing, and the final one is tempering. And let's investigate quenching first. So let me just get the mouse. Okay, so quenching. Okay, so the method of quenching. Okay, when you're quenching a metal, it actually what you're doing is you are heating to a very high temperature. So you're heating the metal to a very high temperature. Okay, so by heating the metal to a very high temperature, what this does to all the atoms, if you imagine, and this is quite a this is not what it actually looks like, but if you can imagine all of these atoms, and I'm drawing the atoms in my metal structure, so they're gaining a lot of energy by being heated, right? So what they're doing, they're still in solid configuration, but because they're being heated, they're all beginning to move out of their particular structures. So in quenching, you're heating those atoms to a very high temperature. So they are beginning to move out of their structure. They're beginning to vibrate and just, move. And then what you're doing, after you've heated it to a very, very high temperature, you are rapidly cooling, followed by rapid cooling. And you usually cool a quenched material in iced water. So what's happening here is that all the atoms within this metal are beginning to vibrate very, very, very quick with a lot of energy, and suddenly they're being exposed to this rapid cooling by iced water. So what ends up happening, the rapid cooling actually ends up freezing the atoms into a smaller grain size. So all the atoms, what ends up happening to the material is that the metal material decreases in grain size. Okay, so quenching involves heating to a very high temperature and then followed by a very rapid cooling. So you're just taking the metal, say you're taking a metal pin. This is an experiment that's commonly done. Taking a metal pin, you're putting it into a Bunsen burner, then you have some ice cold water there by your side. So once that pin is red hot, you're putting the pin into ice water. The ice water very quickly cools that metal pin, and this results in grain size decreasing quite substantially because all the atoms are just frozen into their location. All of a sudden, they were moving around very rapidly, and suddenly you just cool it by exposing the metal pin to an external temperature that's very low, so it freezes them into their spot. And so this creates a very small grain size, okay? And as a result, the reflection of this upon the metal is that the metal becomes very, very brittle. Now, if you can imagine, if you look back at this picture here, if you think about it, as you decrease the amount of grain size, you're increasing the boundaries, okay, the number of grain boundaries. And what this does is it means that the metal will become a lot more brittle. It becomes a lot more brittle because each of these boundaries creates a resistance against other boundaries. So the metal isn't easy to bend anymore because there's so many resistance from all the little grains that it basically only hardens the metal. So the metal, with it quenched, in the process of quenching, the metal becomes hard. Okay. but the downside of it is becomes brittle due to small grain size. So this is very important. The grain size creates the brittleness, the small grain size. Okay, now so sometimes that might be a necessary step, you know, to adjusting the, say you have a very soft metal, you want to make it a bit more harder, you will undergo a quenching process. So the quenching will make the metal harder, but it will also have the downside of making it more brittle. So sometimes brittleness is not, you know, a very functional thing to have with a metal, because, you know, brittle means that if you try to break something, it will just snap. So even though it's very hard, so you can scratch, hardness means that you can take the metal and you can basically use it to scratch the surface of anything and create a dent in it. But the fact that it's more brittle, we'll have a look at how we can reduce that brittleness to make the metal more functional, and that's through tempering, but we will look at that in a second. Before that though, we're going to have a look at this process of annealing. Now, annealing is another method in which we apply heat to a metal. So it's also heating to a high temperature, but what you're doing, unlike quenching, you're not rapidly cooling the metal. You're actually slowly cooling metal. And so what this does, by applying, you know, by heating the metal up and then allowing it to cool slowly, you're allowing all the atoms within that metal to sort of move into their positions. So you're not freezing the atoms, you're allowing them to settle. And what this does is it actually increases the grain size of the metals within the metal. So the grain size is increased. So that's our second point. Annealing causes the increase of grain size due to slow cooling. And the beneficial part of this is the fact that the metal becomes a lot more flexible. So unlike, you know, the brittleness that we have in quenching, the metal you find is able to be more flexible, and you can increase, you know, you can basically bend it a lot more easily, because the larger the amount of grain sizes you have, so if the grains are particularly large, which they will be in annealing, they can actually, it's easier for them to have more motion within that metal. And so they can slide over each other, and the grain boundaries, there's not so many of them, and as a result you can bend the metal a lot more easily. And a lot of the time, you know, chemists do annealing so that there's an increase in electrical conductivity of that metal. So because you don't have as many grain boundaries, those delocalized electrons can actually move through the metal. So it basically increases the conductivity. So due to an increase in motion of delocalized electrons. Okay, so that's quite an important point there. Now that's why manufacturers may want to undergo annealing. Now this is just a figure here to get you to remember the difference between an annealed metal and a hardened metal. So hardened metal, this would be more the quenched scenario, and this is the annealed scenario. So we've got a lot more flexibility in this metal, and in this metal it doesn't want to really bend, and if it does, it will be brittle, so it will probably snap into pieces. Now as I mentioned, to retain some of the, a lot of the time we do want to quench materials. We want the materials to be hard. Okay, in many structures we want metals to be very hard, but we don't want them to be brittle. So in order to reduce that brittle nature of a metal, what manufacturers have done these days is a process of tempering. Now the tempering, this is the final sort of heat treatment that you need to know. And tempering is taking a quenched metal and increasing its toughness. So the difference between hardening a metal and increasing the metal's toughness, a hard metal will just scratch the surface of another material very well. So it will take, you can take a hardened metal and you can scratch the surface of glass, for example. But as I mentioned, a hard metal may still have a lot of brittleness to it. So a tough metal, on the other hand, has the same property, is both capable of scratching the surface, so it's pretty hard, but it's also able to be, to some degree, it has more flexibility, so it can be bent slightly. So what tempering is it's a way to avoids the brittleness, the metal to be brittle, be very brittle. So as I mentioned before, in quenching the grain size gets very, very small. So tempering involves first of all quenching a material, followed by, so first step one would be quench a metal, and step two would be taking that quenched metal and reheating. So this is all under the process of tempering, by the way. So tempering involves taking a metal, quenching it, and then reheating to moderate temperature. So not heating it up too much, but whoops, what is that? Okay, so temperature, that made sense in my head for a second. Reheating to moderate temperature, and then slowly cooling. Okay, so basically what this does is it slightly increases grain size. Okay, so as I mentioned, tempering works with quenched materials and it ends up increasing the toughness of a material. So by slightly increasing the grain size, the consequences of this is it reduces brittleness. And by reducing brittleness, the metal becomes both, it still retains its quality of being hard, but now it's under another category. It's called a tough metal. It's tough because it both has a decrease in brittleness and it still retains some of its hard characteristic. So it's now called tough. And the reason why we would do this, we would temper a quenched metal, is because we still want the metal to be strong, but we don't want it to be as brittle. So if you ever experiment, and you will do so at school probably, you'll take a pin, a metal pin. You might first quench it, so you'll realize that the pin breaks into snaps very easily. If you try to, it's very hard, but it snaps. You may anneal it, the pin, by taking putting a pin into a Bunsen burner and just leaving it on the bench to cool. So that will make the pin very malleable, meaning quite soft, easy to twist around and shape and configure into different ways. But then you may also take the quenched pin and you may reheat it to slightly lower temperature and allow it to cool. And you may put it in the Bunsen burner for only a second or two, and you put it on the bench, and that is hopefully going to temper the material, and it's going to make the pin still hard but a little bit more flexible, so reducing that brittleness nature, and that's what the tempering is there to achieve. So with tempered materials, you can put them into wires. So a tempered material, you can put it into, you can have a copper wire that doesn't bend very easily. It's still pretty tough and it's still pretty hard, but it can still be configured into some kind of shape. So a lot of different applications, a lot of industries use these three heat methods in particular to adjust the characteristics of that metal.